don't know why or how the universe got into the state that we call the Big Bang. We don't know whether the universe existed before that. We have theories that it did, theories called inflation. Before the universe was hot and dense, which we used to call the Big Bang, space and time is still there, and the universe is expanding extremely fast. It's called inflation. And then that period draws to a close, and that expansion sort of slows down and almost collapses and changes, and the energy that was driving the expansion gets sort of dumped into space and changes and ultimately makes the particles out of which we are made. So that's actually the standard model of cosmology now.
What if the universe we live in isn't the first one to exist? What if time itself didn't begin with the Big Bang, but simply reset? For decades, scientists believed that everything, space, time, and matter, started from that single explosive moment. But new research suggests something far stranger might have happened before it all began. And now, Brian Cox has stepped forward with a theory that could completely change how we think about the universe. Keep watching as we uncover what Professor Brian Cox just revealed about what might exist before the Big Bang.
So we do have an idea that we redefine the Big Bang as the hot Big Bang, and it's not the origin of the universe in time. It's the end of inflation. So we don't know whether the universe had a beginning in time, I would say is the correct statement as we are at the moment.
Let's start with what we know for sure. The Big Bang represents time zero, the starting point of everything. In a single instant, all space, time, matter, and energy emerged from a singularity, a point of infinite density. Within the first fraction of a second, the universe experienced an intense phase called inflation, expanding faster than the speed of light in an already expanding space. This event laid the foundation for everything that followed. About 1 second after the Big Bang, the universe existed as a hot, dense soup of particles. Within minutes, the first light elements formed through a process known as primordial nucleosynthesis. At that time, the universe was so hot and packed with energy that atoms couldn't form. Light, or photons, constantly collided with free electrons, preventing it from traveling any distance. For hundreds of thousands of years, the universe was cloudy and opaque. As it continued to expand, it began to cool. Roughly 380,000 years after the Big Bang, temperature dropped enough for electrons to combine with nuclei to form neutral atoms, an event known as the Epoch of Recombination. This changed everything. For the first time, light could move freely through space. The cosmic fog lifted, and light spread across the universe. The same ancient light still surrounds us today as a faint glow visible from every direction, stretched over billions of years into the microwave range. It's called the Cosmic Microwave Background, or CMB, essentially a photograph of the universe as a baby. By observing the CMB, scientists can see the universe as it appeared when it was only 380,000 years old, a newborn compared to its current 13.8 billion year age. This is the oldest light ever observed, a remnant of the Big Bang itself. Discovered in the 1960s, the CMB has been studied in increasing detail using satellites and advanced telescopes. It holds a massive amount of information. The tiny variations in temperature seen across the sky aren't random. They contain the first clues about how matter was distributed in the early universe. Slightly denser areas eventually collapsed under gravity to form galaxies and clusters. The CMB is, in essence, a blueprint of cosmic structure. It shows the tiny peaks and valleys that shape the distribution of matter and provides valuable insights into the universe's composition and geometry. After decades of analysis, scientists have determined that ordinary matter, everything that makes up stars, planets, and life, accounts for only about 5% of the total content of the cosmos. The remaining portion is far more mysterious. Around 27% is dark matter, and roughly 68% is dark energy. These values come directly from precise measurements of the CMB's features. New studies continued to refine this understanding. In March 2025, researchers from the Atacama Cosmology Telescope, ACT, and Princeton University unveiled the most detailed images of the CMB ever captured, 5 times clearer than the previous full sky map made by the Planck satellite. The ACT team even measured the polarization of this ancient light, the way its waves are oriented. This data reveals how much matter moved across different regions of the young universe. Before, we could see where things were. Now we can also see how they were moving, explained Dr. Suzanne Staggs, ACT's director. These images show subtle differences in density and motion within the early gas clouds, the fine details that shaped the structure of today's cosmos. Such findings help scientists understand how the universe evolved from a simple state into one filled with galaxies, stars, and planets. By measuring light that has traveled for more than 13 billion years, we can literally see back to a time when the universe was only a few hours old, in cosmic terms. If the CMB represents the afterglow of the universe's infancy, what happened next? After recombination, the universe entered what scientists call the cosmic dark ages. The fog had cleared, but no new light appeared yet because stars had not formed. This darkness lasted until the first generation of stars came to life, likely between 100 and 200 million years after the Big Bang. These earlier stars, known as population 3 stars, were massive and short-lived. They ignited the darkness and began shaping the young universe. Forming inside clouds of gas that would later become galaxies, they marked the beginning of star and galaxy formation, a period astronomers call the cosmic dawn, when light first illuminated the universe. Today, for the first time in history, we're beginning to observe that era. The James Webb Space Telescope, JWST, launched in 2021, was designed specifically to detect the faint infrared light from extremely distant galaxies. Because light from the early universe has stretched or redshifted into the infrared spectrum, Webb's instruments are perfectly suited to capture it. In just its first few years, JWST has broken records, finding galaxies that existed only a few 100 million years after the Big Bang. One of these galaxies, named MAMZ14, was identified in 2025 as the most distant galaxy ever observed. The light we see from it began its journey just 280 million years after the Big Bang. In other words, we're seeing this galaxy as it appeared when the universe was only about 2% of its current age. The light from that era traveled nearly 13.5 billion years before finally reaching us, and JWST's instruments have now captured it. Since beginning operations in 2022, the James Webb Space Telescope has identified more bright early galaxies than scientists initially predicted. This unexpected abundance has excited researchers and raised new questions about how galaxies formed within the first 500 million years of cosmic history. Each newly discovered high redshift galaxy adds a piece to the larger picture, helping us understand how the universe's structure began to take shape. Take the MAZ14 galaxy, for example. Observations show that it was experiencing a rapid burst of star formation at the time it was seen. Its chemical makeup, containing more nitrogen compared to carbon, is similar to that of ancient globular star clusters found in our Milky Way. This indicates that even during this very early era, star formation may have worked differently than it does today. These findings are forcing astronomers to rethink their ideas about how quickly the small fluctuations seen in the cosmic microwave background could have evolved into fully formed galaxies. How could such large, bright galaxies appear so fast? Were stars and galaxies forming more efficiently than our models predict? Or is there something missing in our understanding of the universe's timeline? With new observatories being developed, scientists expect to peer even closer to the Big Bang, possibly detecting objects from the era of the very first stars. However, no matter how advanced our telescopes become, they will never be able to show us what happened before the Big Bang itself. For that, scientists must rely on theoretical models. Over billions of years, gravity caused matter to clump together, forming a vast cosmic web. Galaxies are not spread evenly throughout space, they form along filaments and sheets, with enormous empty regions between them. This web-like arrangement traces back to the original fluctuations seen in the cosmic microwave background. Our cosmological models, based on the Big Bang theory and an expanding universe containing dark matter, predict that there should be an upper limit to the size of these large-scale structures. A key concept in modern cosmology, known as the cosmological principle, states that on very large scales, the universe should appear roughly uniform, without any single region being dominated by massive clusters or distinct patterns. When averaged across hundreds of millions of light years, every part of the universe should look nearly the same. According to standard theory, the largest connected structures that can form should be about 1 billion light years across. That's why astronomers were astonished to find structures that far exceed those dimensions. In 2024, researchers discovered a huge ring-shaped pattern of galaxies and galaxy clusters, which they named the Big Ring. It stretches about 1.3 billion light-years in diameter and roughly 4 billion light-years in circumference. We're seeing this structure as it existed around 9.2 billion years ago. That's how long its light has taken to reach us. Interestingly, it's located near another enormous feature called the Giant Arc, which spans an incredible 3.3 billion light-years. To give some perspective, the Milky Way's own supercluster measures only about 0.5 billion light-years across. Compared to that, the Big Ring and the Giant Arc are true giants in the cosmic landscape. Detailed analysis even suggests that the Big Ring may not be a perfect ring at all. It could actually be a spiral or corkscrew shape, twisting through space. If we could somehow see it with the naked eye, which we obviously can't because of its distance and faintness, one researcher said it would appear about 15 times wider than the full moon in our night sky. This discovery challenges our current understanding of the universe. The Big Ring is far too large and structured to be explained easily by the known process of baryon acoustic oscillations. Those pressure waves in the early universe could create a large-scale distribution of galaxies, but they would form roughly spherical shells, not stretched-out rings, and certainly not on this massive of a scale. If the data continues to hold up, it might mean that our assumptions about large-scale uniformity need to be reconsidered. Neither of these enormous structures can be easily explained by our present models, says Alexia Lopez, the astronomer who discovered them. Their immense sizes and unusual shapes are almost certainly telling us something important. But what exactly? One idea is that these superstructures could simply be statistical coincidences, random clusters that happen to grow larger than expected. But the odds of finding not just one, but several of these huge formations, including the Sloan Great Wall, the South Pole Wall, and the massive quasar groups, are becoming increasingly small. Another possibility is that they point toward new physics or different conditions in the early universe. Perhaps some unknown process that took place shortly after the Big Bang shaped these megastructures, extending beyond what standard inflationary cosmology can explain. For example, cosmic strings, hypothetical ultra-thin defects in space-time left over from the Big Bang, could have influenced how matter spread on vast scales. If they exist, though still theoretical, they represent one possible explanation for such anomalies. A more radical idea, proposed by the physicist Sir Roger Penrose, goes even further. He suggests that these massive structures could be remnants of a universe that existed before the Big Bang. In Penrose's model, called conformal cyclic cosmology, the Big Bang wasn't the beginning, but rather a transition between cosmic aeons. If that's true, the traces of a previous universe could still be visible in ours. Penrose even proposed that ring-like marks in the cosmic microwave background might be remnants of gravitational waves from the collapse of a previous universe. While most cosmologists remain doubtful of this idea, the presence of such patterns forces us to admit that we may not completely understand the physics of the early universe. Let's recap what we know so far. The Big Bang represents the beginning of the universe's expansion. For the first few billion years, this expansion slowed because of gravity. But in 1998, scientists made a surprising discovery. The expansion was speeding up instead of slowing down. Something unknown, later called dark energy, was pushing the universe outward, overcoming gravity on large scales. Even today, dark energy remains one of the biggest mysteries in cosmology. We know it makes up roughly 60% of everything in the universe, and acts like a form of anti-gravity, driving galaxies further apart. For years, the simplest explanation has been that dark energy is a cosmological constant, a fixed property of space itself, possibly related to vacuum energy. In our current model, known as the lambda CDM model, where lambda represents dark energy, this force stays constant over time, leading to an endless and accelerating expansion of the universe. However, new data suggests that this explanation might not be entirely correct. Observations from the Dark Energy Spectroscopic Instrument, DESI, which has studied millions of galaxies and quasars, shows the dark energy's effect may have changed over billions of years. In early 2025, researchers analyzing 3 years of DESI data found evidence that dark energy may have weakened with time. In other words, instead of providing a constant outward push, its repulsive strength could be slowly fading. According to Dr. Arjun from NSF's Noir Lab, the DESI findings suggest that dark energy might be evolving. If this turns out to be true, it would significantly change our understanding of the universe. It could mean that the cosmic acceleration we observe today will not last forever. As one researcher explained, the force driving the expansion could be losing strength or decaying. This raises important questions about the universe's future. Could the acceleration eventually slow down or even reverse? Might gravity regain control, causing the expansion to halt or collapse in the distant future? We simply don't know yet. But it's becoming clear that the long-standing idea of constant dark energy is now being questioned. Just like dark energy, another invisible yet essential component of the cosmos is under close study: dark matter. Dark matter, which can only be detected through its gravitational effects, is believed to form the framework for galaxies and galaxy clusters. It plays a crucial role in computer simulations that explain how cosmic structures form. Without dark matter, it would be difficult to understand how galaxies developed so quickly after the Big Bang. Despite decades of research, no one's directly detected dark matter particles, and their true nature is still a mystery. The ongoing challenge has led some physicists to consider bold new ideas that could remove the need for both dark matter and dark energy altogether. One such proposal came from Dr. Richard Liu, a physics professor who in 2015 introduced a new model questioning the idea of a single Big Bang. According to Liu, the universe's expansion and structure might not be the result of one event, but rather several smaller mini-bangs or temporary singularities that occurred in sequence. Instead of one initial explosion followed by continuous expansion powered by dark energy, Liu suggests that bursts of matter and energy entered the universe at different times. These brief but powerful episodes could explain what we observe today, replacing both dark energy and dark matter with sudden creation events. During each burst, matter and energy would spread evenly across the cosmos before the singularity vanished. These events would be so rare and brief that we wouldn't observe them directly. They would appear as cosmic flickers that slightly alter the expansion rate and lead to the formation of new structures. Between bursts, the universe would expand steadily without the need for mysterious dark energy. This idea stands out because it revives elements of the older steady-states theory, which proposed that matter is constantly being created. However, Liu's version avoids breaking the law of energy conservation. The traditional steady-state model was rejected because it required continuous creation from nothing, which isn't physically possible. In contrast, Liu's transient singularities appear and disappear so quickly that they bypass such issues. For a fleeting moment, each burst injects energy and mass throughout the universe and then vanishes. Interestingly, this can be described in a way that fits within known physics, though it stretches the limits of current understanding. These temporary singularities would also generate a form of negative pressure, similar to what dark energy produces. Essentially, each burst could trigger a brief period of accelerated expansion, explaining the dark energy effect during that time, while also creating the density variations needed for galaxy formation, the role often attributed to dark matter. Liu's paper suggests that the original Big Bang might have been simply the first of many such bursts, the one that started the cycle. In the standard cosmological model, there was only one creation event. In Liu's model, there are many. It's a major shift from conventional thinking and, as of now, remains speculative. How could we test this idea? Scientists propose searching for specific patterns in astronomical data. For example, tiny irregularities in the redshift-distance relationship of distant galaxies. If the universe truly experienced multiple bursts of expansion, faraway galaxies might not fit neatly along the smooth curve predicted by a model with constant dark energy. Instead, there could be small discontinuities marking those ancient bursts. Whether or not this specific theory is ever proven, its very proposal draws attention to an important point. The Big Bang model, despite its major success, still contains deep mysteries, and solving them might mean going beyond the idea of a single cosmic beginning. But let's return to the central question. What if the Big Bang wasn't truly the start of everything? Modern cosmology actually allows for that possibility. We've already seen Penrose's concept of a cyclic universe, where our Big Bang is just the latest in an endless sequence of universes, each emerging from the remains of the one before it. In this model, far into the future, when the universe has expanded endlessly and all matter has decayed, it enters an almost empty state that curiously mirrors the conditions of a new Big Bang, and at that point, a new aeon could begin. It's an ingenious attempt to connect the end of one universe with the birth of another, though it hasn't gained full acceptance among scientists. Penrose even claimed to have found concentric circular patterns in the cosmic microwave background, features he interpreted as evidence of gravitational events that occurred before our Big Bang. However, most researchers remain skeptical of this claim. Still, the idea of a universe that renews itself in cycles is far from new. Ancient philosophers also imagined an eternal cosmos that repeats endlessly. Some modern theories, like the ekpyrotic model involving the collision of brains in higher dimensions, share a similar idea. Instead of a single beginning, there's a cosmic bounce. These models suggest that something indeed existed before our universe, another one that came before in an endless cycle. Another perspective suggests that time itself began with the Big Bang, meaning that the question of what came before might not even make sense. It's like asking what lies north of the North Pole. For a long time, this was the standard interpretation of general relativity. At time zero, the equations simply stopped working, so one could say that time itself did not exist prior to that point. However, quantum physics challenges that boundary. Some quantum gravity theories, such as loop quantum cosmology, propose that the Big Bang might have been a big bounce, where a previous universe collapsed and then expanded again into ours. In these scenarios, time doesn't end, it continues through the bounce. So there was indeed a before, the universe that existed before the rebound, parts of which might still leave traces in our present cosmos. This suggests that the Big Bang may not have been a creation from nothing, but rather a transition between two cosmic phases. If dark energy is truly changing over time and could one day reverse, as some DESI results hint, then our universe might eventually stop expanding and begin contracting. That could lead to a big crunch, an event that might trigger another explosion, starting the cycle once more. Of course, this remains speculation, but it demonstrates that the question of what happened before or after the Big Bang is not just philosophical, it's an active area of scientific research. Current evidence shows a universe that the Big Bang theory describes remarkably well, yet one that still contains surprises challenging our understanding. So, what do you think? Which of these possibilities seems most convincing to you? Let us know your thoughts in the comments.